Okay, we're going to prove Sanders' theorem today, which I mentioned last time. So there it is in all its glory. Suppose you have a subset of f2 to the n of density alpha. Then A plus A, the sum set, has to contain essentially almost all of a really big subspace or affine subspace, one with codimension polylog 1 over alpha. Okay, and conjecturally, this could be just O of log 1 over alpha, which would be a great result if true. That would be sharp because, for example, A could be a subspace of codimension log 1 over alpha that has density alpha. And if it's a subspace, then forming the sum set doesn't do anything. And if this were true, it would imply the polynomial Freiman-Rouget conjecture and other such nice things. Okay, so we're going to actually come pretty close with this theorem of Sanders and get it to within a polynomial factor. Also, we're going to be using these facts from like lecture 1 or 2 like a million times, and I worry that you may have forgotten them. So please remind yourself of them by staring at the board as I talk. Okay, so there are two sort of ingredients in Sanders' theorem besides what Sanders did. One is called Chang's lemma. That's a well-known old lemma in additive combinatorics. I'll tell you about it in 1 second. And the other is a result or some kind of related results by Crude and Sisask from 2010. And actually, these results have nothing to do with Fourier analysis. They don't have anything to do with additive combinatorics or finite fields or anything. It's just like some probability exercise. Nevertheless, it's a very clever one, and it's probably the main ingredient in Sanders' theorem. So we'll prove that. Okay, so let's start with Chang's lemma. Here's Chang's lemma. So Chang's lemma is not much more than the level 1 inequality from Fourier analysis. It says let A be a subset of f2 to the n with density alpha as before. Okay, actually this A will not be the same as this A, so maybe I should have chosen a different letter, but what have you. And Chang's lemma is concerned with all the large Fourier coefficients of A and their additive structure. So let's pick off the large Fourier coefficients of, we can work either with the indicator of A, or I'm going to work with the density function for the uniform distribution on A. Okay, so it's all the Fourier characters such that the density function for the uniform distribution on A is at least a half. Okay. Then the conclusion is that if you look at these gammas, they cannot span a very large dimensional space. So if you look at the span of all the things in gamma, then that thing has small dimension. The dimension is at most, I don't know, 2 ln 1 over alpha. That's the main thing. Let me write it like this, in fact, 2 over epsilon squared. Sorry, I want to put epsilon here. 2 over epsilon squared ln 1 over alpha. Okay, and just to explicate this a little further, one case you can have in mind is if A is, again, a subspace, okay, of density alpha, then we know that this Fourier transform of the subspace, right, all of its Fourier coefficients are either 0 or 1, and they're 1 on the perpendicular space. That was on your homework several times. And so if you take epsilon to be a half, which is actually what we're going to eventually take epsilon to be, it says that the number of Fourier coefficients which are bigger than a half, which is just all the ones in H perp, span a space of dimension at most constant log 1 over alpha. And in fact, the dimension is exactly log 1 over alpha because H perp will have dimension log 1 over alpha in that case. So somehow what this lemma is saying is that the very large Fourier coefficients of an indicator or a density for a set kind of have to be a bit like a subspace. And as I mentioned, we're actually going to only apply this theorem in the case that epsilon equals a half. So if this is a half, then this will just be O of 1. Okay, as for the proof of this theorem, or lemma, as I said, it's basically just, it almost follows immediately from the level 1 inequality, which says that the weight, the Fourier weight of the indicator of a set at level 1 is like very small if the set is of small density. And in particular, it was on your homework. This was on homework 6. Chang's lemma was number 2. So I assume you all remember it and its proof. Actually, we don't need its proof, just its statement. Okay, any questions about Chang's lemma? We're going to like appeal to it like 50 minutes from now. Okay. Okay, so let's talk about the Kreutzig-Sask theorem, which is sort of the key probabilistic lemma that Sanders uses. Okay, so if I could summarize what Kreutzig-Sask was about in one sentence, it would be somehow that if you have the uniform distribution over a large subset of f2 to the n, and you look at translates of that set, and you look at the uniform distribution over the translates of that set, then this collection of distributions, the uniform distribution over all the translations of A, there's not much room for overlap, and somehow a lot of them have to be kind of similar to one another. Okay, so that would be the final conclusion, but it'll take me a while to warm up to even the statement. So let's get started. Okay, so now we're doing Kreutzig-Sask. So the setting here is script f is a collection of what you might call test functions that map f2 to the n into, let's say, the bounded range -1, 1. Okay, and it'll be the set of sort of test functions for comparing whether two distributions kind of look similar to one another. And I'll make a definition here. I'll say that two density functions, phi and psi, look epsilon delta similar. Okay, vis-a-vis script f. If basically they have the same expectation, or almost all the f's in this test set have the same expectation under the two of them. Okay, so the expectation of little f under phi is within epsilon of the expectation of f under psi for all but at most a delta fraction of f's in this test set. Okay, this notation I like to use sometimes means that the two numbers differ in absolute value by at most epsilon. Okay, so it says that for almost all functions in the test set, phi and these functions have the same, roughly the same expectation under phi and under psi. Okay, so now I state the Kreutzig-Sask theorem. Or some slight modification of it. If capital psi is a collection of density functions, each of the form just the uniform distribution over a big set. Let me say phi b for some b in f2 to the n with density at least alpha, then there exists a subcollection capital Phi prime with, that's quite large. So the fraction of densities in the subcollection is at least this much, alpha to the O of log 1 over delta over epsilon squared, such that all pairs look similar inside Phi prime. Okay, so once you have this collection of test functions, and then you give me any collection of density functions that are kind of big densities, they're uniform distributions over big sets. In fact, it's enough for them to have sufficiently high min entropy, if you know what that means. Then there's some pretty decent chunk of them, such that everything in that subcollection looks similar. Okay, so it's a bit abstract looking, and we're going to apply it in a more concrete setting shortly. Basically, the setting where you fix one set A, namely the A of Sanders' theorem, and your collection of densities is all the translates of A, or more properly, all the uniform distributions on translates of A, to say that a lot of translates kind of look similar. But we can prove this statement in all its generality. Somehow, the picture I have in mind, I don't know if this picture makes sense, but nevertheless, I sort of have it in mind anyway. If this square is like f2 to the n, this phi is like a collection of distributions that are like uniform distributions on big sets. So maybe that's 1, that's like phi b1, and it's like phi b2, and maybe this is phi b3. The uniform distribution over these sets, and because they're so big, I don't know, somehow they have to overlap a lot, or like there's not too much room for them to be. So somehow like a good chunk of them have to sort of look similar to one another. Yeah.
What is the test function?
It's some fixed collection. It works for any fixed collection.
This works for any.
Pardon me?
So this works for any.
Yeah, it works for any fixed collection of test functions. Okay. All right, so the proof kind of goes in 2 or 3 steps. And actually getting a little bit at Madi's question, the first step is to just like focus on like one particular test function. So let me fix some particular test function. And let me even also fix one particular density function in the collection, phi b. And the first thing I'm going to say is that if I sample like a small, okay, so I'm interested in, let's say, the expectation of this f under this distribution. And what I'm going to say is if I just sample a small constant number of elements from set B, like this many, I'll probably, the empirical estimate there will probably be quite close to the true average. Okay, so what I'm saying here is imagine we choose m, which is some constant times log 1 over delta over epsilon squared, uniformly random elements from the set B, and call the resulting set, or actually I'm going to choose them with replacement, so technically I should say multi-set S. Okay, so I want to say that quite likely, if having chosen these elements S, they're like a good sample. So if I were to draw a random element of S and compute the expected value of F under that distribution, it would be close to the expected value if I were to draw from phi b. Okay, so this is like the true average value of f under, when you draw uniformly from B, and this is just like the empirical average. It's just the average of f on these m elements. Okay, and more precisely, we kind of know that Chernoff bound. I'm using here the fact that range is bounded between -1 and 1 implies that this is true up to epsilon, except with probability at most delta. Okay, this probability is over the choice of S. Okay, so if you choose like this many, if you sample this many elements, you're very likely 1 minus delta probable to get an epsilon accurate estimate. So far, so good? Okay. Let me call this event S is a good sample for B. Okay, and now I'll just make like a very minor observation that I'll use Markov. It says that, actually, once you draw S, there's an excellent chance that it'll simultaneously be a good sample for B for most of the Fs. Seems quite likely. What I want to say is that this is equivalent to saying the expectation over S, the fraction of F in script F for which, maybe I don't know if it's equivalent, but let me just say it implies, for which S is a good sample for B is, actually let me say bad sample for B is at most delta. Okay, so you should sort of imagine, okay, let's unfix F now, okay? This is a fact we just saw about every fixed F. Now, don't fix F. Just draw S. For every particular F, we know the probability that S will be like a bad sample for B with respect to that F is at most delta. So, the fraction of F's in script F for which this will hold is at most delta. So therefore, by Markov inequality, the probability over the choice of S that S is a bad sample for B for more than 2 delta fraction of F in script F is at most a half. Okay, this fraction of F's where things go wrong, in expectation it's delta. So the probability that's more than 2 delta is at most a half by Markov. And is that okay, by the way?
So delta is just...
Oh, yeah. It's really like delta and epsilon have also been fixed once.
Oh, right. Yeah, that's right.
They haven't. Well, okay. Yeah, this is really like for all epsilon and delta.
Yeah.
Okay. So let me just invert this. Probably that S is a good sample for B is at least a half. And what I want to claim is that this whole thing, we have a much shorter way to express it using this definition. Somebody want to tell me? Wait. Sorry, I inverted this incorrectly. Bad sample for more than 2 delta. A good sample for at least a 1 minus 2 delta fraction. Well, I mean, if you look at this definition, this this good here as with respect to being approximately the same up to epsilon. Right? This is just exactly saying that the uniform distribution over S and the uniform distribution over B look epsilon 2 delta similar, vis-a-vis script F. Right, just they have the same, F has the same expectation up to epsilon under both of them, at least for all but a 2 delta fraction of little f. Is that okay? Okay. So just to say that, if you have a particular set B, you draw like, constant this many random elements from it, the uniform distribution over B and the uniform distribution over S will like practically sort of be the same from the point of view of most functions in script F, at least, I don't know, with constant probability. Okay. That was sort of part one. All right, let me erase this. Okay, so now here is, so far that was kind of trivial. Here is now sort of the only real idea in the proof, and it's kind of simple too. Okay, that was for like one fixed B. It sort of says, if you have a fixed set B and you draw like a bunch of elements from it, you're probably going to sample B well. Now the thing is, we kind of want to show that all, not maybe all, but like a good chunk of phi B's are similar. So the basic idea is we're going to sample m elements not from any particular B, but just randomly overall. So you should also unfix B in your head. Imagine T is m random elements from f2 to the n. And now, we don't really obviously know that this T is a good sample for any set B. But if I told you that if I gave you the side information that all m elements that you drew happen to come from some set B, then you would know that phi T would probably look similar to phi B. And the point is, B is by definition a big set. So there's kind of a reasonable chance that that will actually happen. So let's, given B, let just EB be the event that everything in T happens to fall into B. So first of all, the probability of this event is not outrageously small. For each element of T, by definition, it's going to fall into B with probability at least alpha, and there are only, well, there's alpha to the m of them. There's m of them, so it's alpha to the m. And furthermore, this is a key observation, the distribution of this random set T conditioned on the event B, the event EB, is exactly the same as the distribution of S from these two panes of the board. Okay, if I draw a bunch of random elements, but then I condition them all falling to the set S, then it's like I had drawn a bunch of random elements from B. Sorry, condition them all falling to B. It's as though I had drawn m random elements from B. Okay, so therefore, for each, let's say phi B in the collection, the probability over this choice of T that phi B, sorry, let's say phi T and phi B look epsilon 2 delta similar, well, there's at least this much probability that this event EB will happen. Condition on that, it's exactly like we're in this scenario. And then the similarity event occurs with probability a half. So this is at least a half alpha to the m. So in some sense, for each b or phi b in your set, your collection phi, there's kind of a reasonable chance that like a totally random set will be like a pretty good sampler for it. And in particular, there must exist some outcome t0 for t, such that the fraction of phi b's in phi for which phi t0 and phi b look whatever epsilon 2 delta similar is at least a half alpha to the m, which now let me remember what m was. This is alpha to the O of log 1 over delta over epsilon squared. Okay. Maybe this alpha should be less than a half or something. Okay, this half is very negligible. Great, so this is basically it. So there exists this one realization of the random choices such that all of these guys, let's say these phi b's, will be the subcollection capital Phi prime that we're looking for. Okay, so for every phi b in this subcollection that we just found, it looks similar to this one particular set phi t0. Okay, and so therefore, this is the last minor step. They're going to look similar to each other by some kind of triangle inequality of similarity. Okay, so let's just check that. Okay, so what we just saw is that for all, let's say, phi b1 and phi b2 in this subcollection, we know that phi t0 and phi b1 look epsilon 2 delta similar, and also phi t0 and phi b2 look similar. Okay, and let's, just to verify that these parameters sort of add, let's remember, this purple is hard to erase, the definition of similar. Okay, so for example, this first statement, luckily that purple arrow is still there. That just means that phi b1 f, this is the expectation of f under the distribution phi b1, is within epsilon of the same thing, the expectation of f under phi t0 for, let's say, except for, okay, for all but an at most delta fraction of the f's. Okay, and maybe there's some other delta, sorry, this should be, say, 2 delta. Okay, maybe there's some other 2 delta fraction of the s where things go wrong for b2, so this 4 delta fraction of the f's. For the remaining s where everything's going right, these two numbers are the same up to epsilon, so we can get that phi b1 f is approximately 2 epsilon, within 2 epsilon of phi b2 f for all but at most 4 delta fraction of f's. Okay, and that's equivalent to saying that phi b1 and phi b2 look 2 epsilon 4 delta similar. Okay, and now we're done. Just adjust the constants on the epsilon and delta, since there's a big O here anyway.
Is this going to be equivalent to proving some sort of an intersection size bound?
I don't think it really necessarily implies that the sets B1 or the sets intersect much necessarily. No, I don't think so.
It depends on how many of them are there.
No, I mean, this fraction is I mean, implicitly there is an assumption in the theorem that phi is large enough, or else this fraction would be smaller than 1 over phi, and in which case there may not be any functions at all.
Right.
So there is some parameter interplay going on which is showing that, I mean, I was imagining it something like for a given alpha there is a large enough phi that the sets will intersect in some minimum amount, and therefore things will.
Yeah, it's a little unclear though, because also you're measuring closeness not in terms of intersections, but like how f looks under these distributions. I have to admit, I still don't fully appreciate. I mean, I don't exactly what's going on with this theorem. Like, I would encourage you to all think it all over and tell me what it really is going on here. Yeah, maybe. I don't know if there's like some information theory explanation, or yeah, there's like some combinatorial explanation. I'm not 100% sure, but in some sense it's an easy proof, so it can't be that complicated. I don't know, any other comments on it? Okay. Well, all right, so that's maybe the key aspect of the Karutzis-esque theorem or theorems or lemma. But we're going to derive a couple of fairly easy corollaries from this, the last one of which will be sort of the Karutzis-esque theorem which Sanders employs. Okay, so let's derive a couple of easy corollaries. I'm going to invent some yet another notation for similarity. So let me say that if I have two functions f and g, I'll say they're epsilon delta close, and I'll write that f squiggle equals epsilon delta g if their values are close. Let me write it properly. Their values are in epsilon, except perhaps on a delta fraction of f2 to the n. Okay, so maybe there's like a small fraction of points where they're totally far apart, but otherwise they're very close to each other. Okay. And here's a corollary of Karutzis-esque. Okay. Okay, so now we're going to do something that I said we'd do eventually, which is we're going to instantiate this where phi is what you get by you take the uniform distribution over A and also consider uniform distributions over all the translates of A. And actually, for our collection script f, I guess it no longer exists, but we're going to actually do the same thing. We're going to fix one particular function f and sort of consider all its shifts by a translate as well. Okay, so in this theorem, we're going to fix one particular f and also one particular a with mean alpha or density alpha. And the conclusion is that there exists a big set of translates z okay, where the density of this z is this expression we've seen before, alpha to the log 1 over delta over epsilon squared, such that, okay, the following thing holds. Phi little z plus a convolved with f is close to phi a convolved with f, epsilon delta close, for all little z and big Z. Okay, so this is kind of the key conclusion right here. somehow says with respect to this, one basic test function f, the uniform distribution over A and the uniform distribution over this shift of A kind of look the same. Okay, at least for like very many shifts. And this is where like we've sort of got back into additive combinatorics. This is somehow saying that like, I don't know, A is somehow similar to many shifts of A. And that's kind of vaguely like saying A is like a subspace or a coset, because if A were a coset, it would be true that whenever you shifted it by something that was, let's say A is a subspace, then whenever you shift it by something also in the subspace, of which that's a pretty large number of shifts, you get sort of the identical behavior. Okay. All right, so let's prove this. And it's kind of amazing that really this only uses the fact that A is a big set. Somehow has the same feeling as that weird picture I drew up here, where the box is f2 to the n, and like you have this uniform distribution over A. Somehow if you start looking at the shifts of all the translates of A, they somehow have to overlap or something, for some definition of overlap. Okay, so let's prove this corollary. Okay, so as I said, we're going to apply crude sysask with phi equal to just a set of all density functions for shifts of A. Okay, and all these are uniform distributions over sets of density exactly alpha, so this applies. And we actually also need to specify this class of test functions, and that'll just be all the shifts, if you will, of f. Where I'm using some notation that was on the homework, f plus t of x is just defined to be f of x plus t. Okay, so it's f where you like rotate the domain by plus t. Okay, so now these are our two choices. Now let's just apply the theorem. So we get that, well, a big chunk of these guys look similar. Okay, so phi of z plus a and phi of, let's say, z prime plus a look epsilon delta similar, okay, with respect to script f, for all z and z prime in some set z, where mu of z has the required density. Actually, let me call this z prime. Okay, so now let's focus in on what, we're just working through the definitions here. Nothing surprising is ever going to happen. Let's just sort of remind ourselves what this looks similar means. It'll, more or less give us this. Okay, so i.e., we get that, well, let's just say that phi z plus a inner product with f plus t is close to phi z prime plus a f plus t. Okay, that's at most epsilon for all, but at most the delta fraction of t. Okay, and what is this quantity here? Let me change colors. I claim this is just equal to phi z plus a convolved with f at t. Okay, because what happens here, you draw randomly from this distribution, and then you compute f, call that draw x. You compute f plus t at x and multiply. And that's similar here. You draw, to compute this, you draw x at random and do this phi at x times f at t plus x. Okay, this is all like lecture 2 stuff that I was hoping to remind you of at the beginning. Okay, and similarly, this is phi z prime plus a involved with f at t. Okay, so in other words, phi of z plus a star f is epsilon delta close to phi of z prime plus a star f. Okay, by definition of epsilon delta close. So that's almost what we want. We got this big set z prime such that for any two z and z prime in that set, these two guys are close. But what we really wanted was like a set of about that size such that anything that looked like this was close to what you'd get if you just had a. Okay, but that's going to be easy to achieve because this epsilon delta closeness is a translation invariant notion. Okay, so to fix that, we're almost done. Fix some z naught in z prime, just any one at all. It can be arbitrary. And then for all little z in z prime, okay, well, we have just what we saw. We have this. Okay, so these two functions are close. So now if I have two functions that are close in the sense that I just erased, and I just change both of their domains by adding t, it's still true. So what I want to say is I can do this if I want. When I'm using this notation, right? That just shifts this delta sets where they might be haywire apart from one another by translation by z0. All the other points, they're still within epsilon. Okay, but then if I do that, this is again this is the experiment. You draw from this distribution, you evaluate f of x, but now instead you actually evaluate it with plus z0 in the domain. So if you think about it for 2 seconds, this function is literally the same as phi z0 plus z plus a star f. And similarly here, you can bring the z0 in, but then it cancels out. So you get phi a star f. Okay, so having fixed this z0, you know that for all z, if you take this, it's very similar to what you get if you translate by z0 plus z. Okay, so therefore, we can take the final z that we desire for this corollary to be z0 plus z prime. Okay, which has the same density as z prime, so it has the density we want. Any questions about that? Okay, so we're almost done with Kritz's ask. Okay, in fact, that's the main, a main result of Kritz's ask. And now we get one further corollary, which is very nice. And it's a bit hard to explain succinctly why it's nice, but if you eventually see the whole proof of Sanders and look back at it, you'll see that this corollary we're going to do now is an important step. Actually, in the interest of time, I'm going to do this. Let me give the proof as an exercise. It's going to look very believable. Okay, so what we kind of know now is you have this big set of translate z, and you kind of know that if you look at phi a star f, and then you translate a by z, you still get something that's close. And what I'm going to say is I want to say by some kind of triangle inequality, if I translate by like adding in 2 little z's from z, it'll still be close, maybe up to a factor of 2 or 3 z's or so forth. Okay, so it's just for all w in the sum set z plus dot 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 plus z k times. Okay, this is really for all natural numbers k. Phi w plus a star f. Let's say k epsilon k delta close to phi a star f. Right, I think well, the whole proof is just this much in my notes. It's just uses an observation that's similar to this, and like the triangle inequality, basically to iterate this to get that. Okay, and this is sort of an even better statement because it kind of is more like the lines of like pushing A or maybe pushing Z to be like a subspace, because A is not sort of just invariant under this like big set of translations Z in some sense, but it's even invariant under like doing like many iterated translations from Z. And now it really even more sort of feels like somehow the only way this can be happening is if A is like a subspace and Z is similar to A or similar like that. I mean, you'd think that this would be like a really big set, like a much bigger set. Just very unlikely, perhaps, that 5A would sort of remain kind of invariant under translations by anything in this big set. Maybe the only way this can be happening if Z is kind of like a subspace itself. Okay, this is all kind of hazy intuition, but sometimes this hazy intuition is better than no intuition. Okay, so this was also done by Krut-Sisask. In their 2010 paper, this is Ernie Krut and Olaf Sisask, by the way, and this finally is the result that is used to prove Sanders' theorem. Okay, any questions? Okay, since I'll probably eventually erase this, let me just put it into here. This is really for a fixed f and A with density alpha, which is the assumption. And the density of Z here is this alpha log 1 over delta over epsilon squared. Okay, so now we're going to prove Sanders' theorem. So I'll remind you what that is. We're given a set A of density alpha. Okay, we want to show that A plus A contains 99% of an affine subspace with codimension polylog 1 over alpha. All right. Okay, so proof of Sanders. Given A, get this set Z, where all the parameters F, epsilon, delta, and K will be named later. Okay, F will also have something to do with A. It'll be the indicator of A plus A, in fact, to give it away. Okay, we're given some A in Sanders. Let's apply this powerful theorem to kind of get this big collection Z under which, even if you iterate it many times, A kind of remains invariant under a translation by it. The first step of Sanders is to fix a little bit this. So we have this closeness where it's within K epsilon except on this small set K delta. Okay, and we first want to get rid of this small set K delta so that there's no aberrant set at all. And the way you're going to fix that is by actually averaging out both functions again by the large density function phi of A. So let's say here's the picture. There's some aberrant set here of size K delta. And I'm actually going to look at the set A itself, which maybe does or does not contain some of that set. Its density is alpha. And okay, what I want to say is, okay, we have phi w plus a star f. It's kind of close to phi a star f. And what I want to actually do is average both of these functions over a. And I want to upper bound this. So these two functions, we know they're within epsilon of each other like everywhere in this whole box except on this little set here. And in this picture, what is this? Right? This is literally the expectation over a, little a drawn from a of this function at a. Okay, so for like most draws of little a, these two numbers, this guy at a, little a, and this guy at little a, will be within epsilon. And, you know, if little a happens to land in this set, then it could go wrong and they could differ by like 2, because f's range is -1 to 1. Okay, but I'm going to arrange for k delta to be even small compared to alpha. Okay, so what I want to say is that this thing will be at most, you know, epsilon. We can't really do much about that. Plus, with probability k delta over alpha, I'll pay 2. Okay, the worst thing is if this whole set is inside capital A. Also I screwed up because the closeness is k epsilon, not epsilon. Okay, so I should have written k here. Okay. All right, and I want this to be really small. This error. So I'm going to claim that this thing is at most 0.005 if I choose epsilon and delta, and eventually also k appropriately. If, let's say I'm going to take epsilon to be 0.001 over k. Okay, still k I'm going to choose later. And I'm going to take delta to be, I don't know, 0.001 alpha over k. Okay, so then if I take this, then this will be 0.001, and this will be 0.002, so that's 0.003. It's less than 0.005. Okay, and this is going to be small. And the other thing I'm going to choose, let me now choose, in fact, f, so that this thing is 1. So this is finally choose f, just to be the indicator of a plus a. Okay, so this thing, remember, is equal to, it's the same as phi a star phi a inner product with f. Okay, which is, this is the density function for first draw from a and then draw again from a and add them up. So this is, by definition, the expected value over a1 drawn from a and a2 drawn from a uniformly of f of a1 plus a2, okay, which is 1 with our choice of f. Okay. If you draw something from a and another thing from a and add them, then it lands in a plus a by definition. Okay, so therefore we can conclude that this thing is at least 0.995. And I'll do the same trick of moving this phi w plus a over to the other side. Well, let me stick in our definition of f. Okay, and remember what's the definition here. What's this saying? First you draw from A, then you draw from A again, but you get w plus A, and you look at w plus A1 plus A2. Okay, let me write it. This is the expectation over A1 and A2 drawn from A of the indicator of A plus A on w plus A1 plus A2. Okay, in other words, it's the probability that this thing lands in A plus A. So somehow for this large collection of w's, if you draw two things from A and add them, but then also add w, you still have like an excellent chance of landing in A plus A somehow. Okay, so now it feels like we're getting somewhere. Okay. By the way, now that we've set some parameters, epsilon and delta, actually, now we've set delta f, we've set epsilon, we've set delta. The only thing we haven't set yet is k. So let's clean up the situation a little bit. So let me just say, by the way, what are we saying about the mean of this set, or the density of this set z? This is greater than or equal to. Okay, so it's at least. Okay, let's see. Let me first write it as exp minus O of log 1 over alpha times log 1 over delta times 1 over epsilon squared. Okay, here I've not done nothing. I've done nothing. It's just the same as this. So I just push the alpha up into the exponent. Okay, and epsilon is like constant over k, and delta is that thing. So we get exp minus O of log 1 over alpha, and then like log O of k over alpha, and we get k squared. Okay, and now we just say we'll be taking k to also be like log 1 over alpha. Okay, so we get 1 log alpha, 1 over alpha, we get 2 more. And this is like log of log over alpha. That's negligible, so it's still like another log 1 over alpha. So the measure of z is indeed at least something that should look familiar, exponentially, at least exponentially small in log to 4th 1 over alpha. Okay. Questions? Okay, let me make one more additional observation here. I'm actually going to take this statement and weaken it a little bit. See, in this experiment, I'm saying, this is the experiment where you draw a random thing from A, and then you draw a random thing from A, and then you can add any W you want. And I tell you that that's at least 0.995. I'm just going to remember that that holds true if you form W by drawing randomly from Z k times. Okay, so W is not going to be a worst case element of this. It's going to be like a random one given by chosen k random things from Z. So what does that mean? It's like saying that this is, in particular, implies same experiment, but now, well, this is like, again, drawing from A, but now I'm going to draw k times randomly from Z. So that's phi Z tensor or convolved with itself k times. Okay, so this is actually shorthand for k times convolution of phi of z. Okay. Actually, let me write that over here. Okay. Great. All right, next step. I kind of told you before that, we sort of feel that the only way this could happen, that like A is sort of invariant under all of these shifts by even like this huge subset of Z, the only way that sort of looks plausible is Z is sort of like a subspace itself already. And so now what we want to actually do is sort of take this statement and make it also true for like, we want to replace Z by an actual subspace that's somehow related to Z. Okay, we want to like pick the subspace that's sort of most similar to Z and see what we get. And we do that by using Chang's lemma. Okay, so we're trying to replace Z by a subspace or replace it by the most similar subspace. So let's do what we do in Chang's lemma. Let gamma be all the Fourier characters such that the distribution, the density on Z has like a huge Fourier coefficient on gamma. Okay, if Z really were a subspace, this would really just pick out its perpendicular subspace. And let's let H be the span of this. Okay, so this is our subspace replacement for Z. And what Chang tells us is just that the dimension of H, the dimension of the span of this is at most, this is like we chose the epsilon to be a half, it's just O of log of the density of Z. Okay, and the density of Z was this, so it's like O of log fourth 1 over alpha. Okay, so H is like this huge subspace, just like what we're looking for. H is like a tiny subspace. So the huge subspace we were looking for will be like H perp. Okay, so we'll show that A plus A contains 99% of, let's say, a translate of H perp. Okay, and this will complete the proof. All right. Okay, and what I'm going to show in a second is that basically I want to say that somehow since H is similar to Z, I can sort of stick a convolution by H perp in here, and it doesn't change things very much. Okay, so let's say this, whereby this I mean A plus A will contain 99% of translative H perp, will follow from this happy face inequality, which is this. Phi Z convolved with itself k times, convolved with phi A, convolved with phi A, convolved with 1 A plus A, is within, to 0.005 again, the same thing when I also convolve with H perp. Oops, wait a minute. Okay, so the very last thing I'll do in the last 7 minutes will be prove this inequality. Well, that these two numbers are close. And now I'll deduce the remainder of the argument, namely this statement, assuming that inequality. Okay? Okay, so obviously this thing implies that, well, we have this fact here. And we're just saying this thing is also close, so we get that 0.99 is less than or equal to this thing. Okay, this is actually a funny conclusion. Let me say exactly what this is. This is like some crazy probability distribution. You draw like all sorts of stuff in a weird way. You finally also draw something from H perp, and then finally you ask, what's the probability that it's in A plus A? Okay, it's like the expectation over, let me say, H drawn from H perp. Expectation, this is, draw K things, all uniformly and independently from capital Z. Then we draw like A1 and also A2 independently from A. And finally, we look at 1 of A plus A of the sum of everything. H plus Z1 plus ... ZK plus A1 plus A2. Okay, and now we just observe, if we do this crazy probability distribution where the very last step is like adding a random thing from H perp, we get into A plus A, capital A plus A, with probability at least 99%. So there exists like an outcome for like all this crapola, which is still good for us. So there exists some particular y of the form, like Z1 plus ... some outcome. Zk plus A1 plus A2, such that, just by averaging, 0.99 is less than or equal to the expectation over little h drawn from H perp of 1 A plus A, H plus Y. Okay, and this is really, well, let me just write as the probability of little h drawn from H perp that H plus Y is in A plus A. Yeah, so this is like saying if you take a random element from this giant subspace H perp, translate it by Y, there's a 99% chance it's in A plus A. So like, if you look at Y plus H perp, some subspace, you draw randomly from in it, A plus A contains 99% of it. In other words, A plus A contains 99% of the affine subspace Y plus H perp. Okay, which is the desired conclusion. Okay, so the last step is to justify this. I'll actually use a little Fourier analysis. Okay. Great. Okay, so let's see. The left-hand side of this inequality. Now let's finally use Fourier analysis. It's the inner product of two things, so it's like the sum of the products of the Fourier coefficients. And like if you take the Fourier transform of a big convolution, it replaces all the convolutions with like multiplication, right? So what I'm saying is the left-hand side here is the sum over all Fourier characters of, well, we get like phi z hat gamma, and we get it like k times. Okay, and this is ultimately why we cared about the, like the k times iterated subset of z. some set of z, in order to get this k power up here. And then we get a twice. So we get phi a hat gamma squared. And then finally we get 1 a plus a hat gamma. And the right-hand side is the same, but with an extra factor. It's like phi h perp hat gamma. Okay, now this came up a million times on your homework. We know the Fourier transform of a subspace. Okay, it's the density function for a subspace. It's like all the coefficients are 1 if it's in the perp of this thing, which is just h, and is 0 otherwise. Okay, so on the left-hand side and the right-hand side, here's the left-hand side. And basically, on the right-hand side, you just zero out all the terms which are not in h. Question, Misha?
They're in H perp. Does that mean that they're not in H?
This is really h perp perp here, which is the same as h. So this is true. And so now what I want to say is that left-hand side minus right-hand side is equal to, in absolute value, the sum over all gammas that are not in h of this thing. Is that okay? I think it's okay. No, it's okay. I mean, I don't know. You don't buy it? Sure. Okay. All right, good. Great. So, yeah, there's like two lines to go. Let me just use the triangle inequality to warm up. Phi z hat gamma to the k. This thing's already the square of something, so I can just leave it. It's already non-negative. And then we have the coefficient of indicator of a plus a and absolute value. Okay. All right, let's see. This is a 0-1 valued function. It's like a Boolean valued function practically. So all of its Fourier coefficients and absolute value are at most 1. Seen that many times. So this is just at most 1. I'll just get rid of it. And great. Finally, this part. This is key part. It's going to make this error term small. You see, by definition, every Fourier coefficient of z is small, smaller than a half, unless it's in gamma. But if it were in gamma, it would certainly be in h, the span of gamma. Okay, but it's not in h in this sum, so it's not in gamma. And so all of these things are at most a half. Okay, which is awesome because we're raising them to the power of k. That's why we love that k. It kills that term. So this is at most, a half to the k. Sum over gamma not in h, phi a hat gamma squared. Okay, and then, this last thing here, sum over gamma naught in h of phi a hat gamma squared. It's at most the sum over all gammas of phi a hat gamma squared, which is by Parseval equal to the expected value of phi a squared, which is equal to what? I asked you this exact question last class. Sorry? Yeah, 1 over alpha. Great. So this thing, sort of at most 1 over alpha. Finally, I don't know if it's still written here, but we decided to take k to be theta of log 1 over alpha. Which is great. If we make this constant large enough, we get a half to the power of log 1 over alpha. And we can make that kill this alpha. So we can make this 0.005 or whatever it was supposed to be. OK, that's it. Any questions?